Dynamic equilibriums occur where you have a reversible reaction. Certain conditions have to be there for this to occur. First of all, it's got to be a closed system. That means that none of the reactants or products can leave this situation. So it couldn't happen if some of the products were gases. It would have to be in a closed, sealed container. Okay. Otherwise, you'll never reach equilibrium. How do you know when you have a dynamic equilibrium? The concentration of the reactants and products remain the same. So it looks like once you've reached equilibrium, it looks like the reaction stopped, but it hasn't, because what's actually happened, the third point, is that the rate of the forward reaction is the same as the rate of the reverse reaction. So they're constantly changing. That's why it's called dynamic equilibrium, because nothing's staying still. It's constantly changing, but it's changing at the same rate, so the concentrations stay the same, even though the forward reaction and back reaction are still occurring. Now, an important thing about the concentrations is that they don't have to equal each other. The concentration of A and B and C and D do not have to all be the same. They can be different. It's just that they stay to themselves, they stay constant. So, for example, we could have a lot more reactants than we do products, but once it's reached that situation, the forward and backward reaction are going at the same rate, so that the concentration of reactants stay the same, the concentration of product stays the same, but not equal to each other. Okay? In this scenario, we would say the position of equilibrium lies to the left, because the equilibrium is set up in such a way that we have more reactant than we do product, or higher concentration of reactant, let's say, than the concentration of product. Or it could be that the position of equilibrium lies to the right. So in this situation, we've got a higher concentration of products than we do reactant, but the concentrations of each of them is staying constant. They're not changing, but the forward and backward reaction is still occurring, but they're occurring at the same rate to keep those concentrations as they are. So in this scenario, position of equilibrium lies to the left. Here, position of equilibrium lies to the right. So what affects where the position of equilibrium lies? That's what we're going to look at next. And Le Chatelier's principle, he's obviously a French scientist, he said, when a system in dynamic equilibrium is subjected to a change, the position of equilibrium will shift to minimise the change. So whatever you change about the reaction, the equilibrium will shift to minimise what you've just done. So what can change it then? There's three main things here. Concentrations of reactants or products. We could add a reactant or take a reactant away, or add a product or take some product away. So we're affecting the concentrations. Pressure. We can change the pressure. This is just looking at reactions with gases, obviously. And temperature. We could change the temperature of the reaction. Okay, so here we're going to look at the first point, concentrations of reactants and products. So I'm just going to focus on A here, it's a reactant, but what I'm saying here could equally hold true to the other ones as well, like B, C and D. So the concentration of A is increased. The Chatelier's principle says that the system will oppose this. If I increase the concentration of A, the system, it's in equilibrium, will oppose this by decreasing the concentration of A, and it will do this by moving the position of equilibrium to the right. So position of equilibrium will go this way, and that means we'll get more products formed. So the A that I've increased will be used up and form more products, and regaining that position of regaining that equilibrium. If the concentration of A is decreased, the system opposes this change and increases the concentration of A. So the position of equilibrium moves to the left to replace the A that I've taken away by decreasing it. And so we get more reactants, and so we must be getting less products.